So this is a collaboration between the University of Vienna and University of Augsburg. And it's a long-time cooperation. So the first part was also presented by Timo. And now we wanted to investigate a bit further. But before going into the main motivation, I just want to give a short recap on the topologically protected spin textures. And we will mostly concentrate on the Bloch skyrmion, which is a local whirl in the magnetization. So if you have an outer region where we have a ferromagnetic state, where the magnetic spins are pointing down, then at the center we can have a whirl in the magnetization such that we obtain a quasi-particle-like structure, spin texture, which has this topological protection. If we take now, if we would sample the magnetization along this line, then we would obtain Bloch walls, thus the name of Bloch skyrmion. For many, the real skyrmion, the NEA skyrmion, which comes in a chiral system, which is usually stabilized in the using interfacial DMI. In this case, if you sample the magnetization along this line, then we would have nail walls. So that's why. Because this is let's say the Bloch skyrmions, they're not in a pure chiral system, but depends. So they're usually stabilized in bulk DMI systems with P20, for example. And if they are dipolar stabilized, they rather refer to magnetic bubbles of type 1. And we also have type 2 bubbles, which have only half of charge, and they basically have this surrounding, so it goes basically down and up and then down again, but we do not have this full rotation of the, let's say, perimeter. And in addition to this, we also have the antiskyrmion that we will also investigate in this talk. And now the basic idea is that the antiskyrmion is a topological counterpart to the skyrmion. And if we say that this has a topological charge of +1, this one will have -1. And we will basically, let's say, we will see here an iteration of a Bloch, also of Bloch and nail walls, such that at the end we form an antiskyrmion. And the one thing that we will also use is the magnetic vortex. It's maybe in one of the most known structures that have been investigated intensively. And when it comes to the motivation of our work, is that, as we have also seen yesterday in the very nice talk by Timo, was that we were using iron gadolinium multilayers, where we have inserted additional iridium layers, and we were able to observe using Lorentz stem and then later in simulations counterclockwise Bloch skyrmions, clockwise Bloch skyrmions, as well as first and second order antiskyrmions in the same system. In our micromagnetic simulations, we have seen that we can start with a domain morphology where we have strap domains with tripods, or like chiral or not chiral, let's say, domains or stripe domains, and upon application of an external field out of plane, then we can shrink down these magnetic domains, and the domains, so the stripes without the chirality, they will break down into trivial bubbles, into type 2 bubbles, whereas those with a chirality would then break down into Bloch skyrmions. And if we have tripods, we could also obtain antiskyrmions. And we have also seen yesterday that we have a well-known recipe to obtain antiskyrmions, so dipolar stabilized antiskyrmions. And here also a closer look on how these two structures could look like. And it's not very visible here, but the stability also differs. So usually the antiskyrmion is a bit less stable. But in this system that comes basically with a problem, namely, we also talked about, so we just had a very nice presentation talking about racetracks, and there was the idea that you should be able to write it, move it, and control it. And this is something you just cannot do here. You have skyrmions, antiskyrmions, bubbles everywhere. It's very difficult to put them on a lattice, because if you say that so there is this method that you can apply an in-plane magnetic field, you can force your helices, or you can force your stripe domains to be along one direction before applying the out-of-plane field. But then you lose the chirality, and then you will only have bubbles, but no Bloch skyrmions, and so on. So it's a bit more tricky. And the more important one maybe would be also that we cannot control the chirality of the skyrmions. You have no power to say, okay, I want to have a clockwise or I want to have a counterclockwise skyrmion. and you cannot choose one of the skyrmions and delete them, right? So you cannot just access a system and just delete them. And that's what we are trying to solve. We want to have a system where we can control this. And for this, we are using magnetic metamaterials. And the basic idea of using a metamaterial is that you combine two systems. One of them you know how to control, and the other one you don't. So, and in our system, we will be using our iron gadolinium as the purple layer and as a skyrmionic layer. And then we are patterning nanodot lattice. And the nanodots are out of permalloy. And we want to, because we know how to play around with permalloy, we know how to control permalloy, nanodots and the race, they've been intensively investigated. We hope to be able to control the structures underneath. And of course, we are then not limited to nanodots. We can also have nanosquares. But I will not talk about this. But I would rather talk about the anti-square lattice, if you wish, but which is basically very similar to an artificial spinized lattice, which then it's an interconnected artificial spinized lattice. It's just a square lattice. And for the first part, so this is a pure micromagnetic simulation work, let's say. And we have patterned, let's say we have designed our two materials. And in each, so it's a finite difference simulation. In each cell, we start with a random magnetization state. And we first relax the structure, so which means that we are solving the Landau-Lifshitz-Gilbert equation numerically. And we include energy terms from demagnetization, from uniaxial anisotropy, so PMA, and exchange. So we don't have any DMI in the system. If we relax the structures, then we can see that in the permalloy lattices, we are observing, of course, vortices. So we have chosen the critical dimensions for the permalloy nanodots to be able to host stable magnetic vortices. And you can see that we have blue and red dots. It will be a bit more clear in the next slides. But you can see here, if we don't apply any out-of-plane magnetic field, then we have the polarization of the magnetic vortex core can be either up or down. And we can see that underneath in the skyrmionic layer, we have a structure which starts to look a bit more like a lattice. So then we apply an out-of-plane magnetic field. We go up to 100 millitesla. And at the end, what we're observing is that we can relax a skyrmion, let's say, lattice. But because we started from a random state and we did not really manipulate the permalloy layer on top, what we see is that whenever we have the polarization of the magnetic vortex core, which is not aligned with the magnetic field, we have a skyrmion underneath. And whenever the polarization is parallel to the applied magnetic field, then we do not have a skyrmion. And here we can also see that so even though we apply 100 millitesla out-of-plane field, we are still having very nice magnetic vortices. So we see that we have a little bit of an out-of-plane component, but the decisive part, which is the magnetic vortex core, it's still in the system. If you now have a closer look, then we can say that we have here the magnetic vortex, which has the polarization parallel to the applied magnetic field. Then we do not see a skyrmion. And then in the next one, where it's anti-parallel, then we see the skyrmion as plotted here by the magnetic induction map. And if you would then sample the magnetization along this line, then we can see here very nicely that whenever the vortex layer, so where the magnetic vortex core points down, so then we obtain a skyrmion. And whenever it points up, then we do not have a skyrmion. So this is, as you see, that we start with a random configuration. We just like relax the structures. So now we also want to obtain this beautiful lattice where we have a skyrmion at exactly, basically everywhere we have a non-dot lattice. And experimentally, one can achieve this, let's say, by hitting, so permalloy and the iron gadolinium multilayers, they will have different Curie temperatures. So if you heat it up only to, let's say, 300 or 400, to 400 degrees maybe, or 400 Kelvin, let's say, or 400, 500 Kelvin, then the permalloy will still be ferromagnetic, but iron gadolinium will already become paramagnetic. So then you can manipulate at high temperatures. You could manipulate the permolar disks, arrange them in all in a clockwise manner by applying an X field whatsoever, and then apply a positive field, and then also decide over their polarization. And then cool back down, and then obtain a full lattice of skyrmions. And because we can also pattern the nanodots in desired, let's say, lattices, so we can have a square lattice, we can have a hexagonal lattice, and so on, we can also choose how to exactly pattern this. In this way, we just wanted to show that we can have a full lattice. So we put all to have the same chirality and also the same polarity. And if you have a look at the cross-section, we can see that whenever we have a skyrmion in the skyrmionic layer, the magnetic vortex core rather diffuses into the skyrmionic layer. And maybe at this, I forgot to say, but we do not have any interfacial coupling, so we do not have any spacer layer in between. This is not like the artificial skyrmion lattices that have been already done previously, where you basically have you have some nanodot, and then you have a spacer layer which couples them ferromagnetically to the 1 or 2 nanometer skyrmionic layer underneath. But the dimensions are rather 30 nanometer, so this is wrong, but 30 nanometer of permolar disk, and then 50 nanometer of a skyrmionic layer. And we can see here that it's fully diffused into the system. In the case where we do not have a skyrmion, then the magnetic vortex core, which points up, is just like more, let's say, a bit more constant, and only when the skyrmionic layer starts, it starts to diffuse a little bit. Okay, and now one more time, we can see that if you plot now the magnetization sampled along the x direction, we can see that whenever we have a vortex core, which is antipolar to the field, then we obtain the skyrmions underneath. And with the same chirality, as you can see here, they all have the same chirality underneath. But as I said, so I also worked a lot on artificial spin ices, so I wanted to maybe see how such a structure might behave. And in principle, it's also possible to relax vortices in these structures. And note that we have, again, about 30 nanometer thickness. And I was also a bit inspired by the work of Sebastian Gliga, where they had, where they showed micromagnetically that they can also switch by a field, by a pulse field, by a field pulse. They can switch the magnetic, the core of a magnetic anti-vortex. And what they have done is that they basically apply a short pulse of about 100, 200 picoseconds, and they were able to reverse the magnetic vortex core. So I thought maybe this is something that we can somehow take, so we can also try later to use it to our favor, which I will discuss in a moment. But the basic idea is that to now create basically the ground state of the artificial spin ice lattice, which would be the ice rule. So we have magnetizations in the let's say, the host material and in the metamaterial, where 2 magnetizations points in and the other 2 point out. So we have the 2 in, 2 out rule. It's the so-called ice rule. And this is the ground state of this lattice, because the magnetization will then build closed loops. So we have to go here to the right and here go back up to have everywhere these type 1 vertices. And in this case, we build the closed loops, and that's why we have the long range or the ground state. But in spin ice and artificial spin ice field, people do not use interconnected lattices, but rather stadium-shaped like islands and whatsoever. But here we have the interconnected system. So whenever we have this structure, the magnetic configuration is then forced to build an anti-vortex. And the goal was to obtain the antiskyrmion underneath, which we can see here at, again, exactly wherever we have the anti-vortex core. So we're making use of the exchange interaction to couple the, let's say, to imprint a little bit, or like help to nucleate the antiskyrmions. Again, we can choose here the, let's say, the direction by the sense of rotation. So as you can see here, they are 90 degrees rotated, the antiskyrmions, which might be actually helpful, but I will maybe give that information later. And we can now have, again, a closer look. We can see here that we have the anti-vortex, and this one is the antiskyrmion. And if we sample the magnetization along this line, wherever we have the anti-vortex core, we can also have an anti-skyrmion in our skyrmionic layer. but there is a one point that it's missing, and namely, okay, but not yet, so I forgot about this slide. So we can again have the skyrmion lattice as we wish. We can control the direction, we can control their existence, and this diffuses a bit more. It's a bit more straight, but it comes because the lattice is basically a bit more constrained geometrically. And this is maybe the more interesting part, because as it was also said, so you also have to write them, but also delete them, right? And you want to be able to delete them by command. You want to delete them energetically, you want to consume less energy as possible. And for that, we have again our nanodot, and we apply the out-of-plane field to stabilize the skyrmion. Then now we apply a pulse of magnetic field, which is about 200 picoseconds. And it's also only, I guess, 50 millitesla. And what happens upon application of this pulse is that we create the well-known vortex and divortex pair in the nanodot, which then destabilizes a bit the antiskyrmion. But ultimately, this vortex and divortex pair will then collapse and then reverse the magnetic vortex core, which will then delete the skyrmion underneath. So if you remember, the skyrmion was only stable, or let's say it's stable as long as this vortex points opposite to the magnetic field. So when you reverse the polarization of the magnetic vortex core, you automatically delete the skyrmion. And this is allowed topologically because the total topology of the system does not change signs. So you have the skyrmion, which has the +1, and then you have the vortex, which is 0.5, and then in total you do not change signs. That's why it goes over. So you don't need any Bloch point formations to annihilate the skyrmion. And we want to do the same for the anti-skyrmion. And we apply again the pulse of magnetic field. We have the magnetic anti-vortex core. Then we apply the field. We switch the anti-vortex core. And again, without switching the sign of the total topology, we can delete the anti-skyrmion. To briefly summarize everything, we have seen that we can use metamaterials to pattern, let's say, to obtain arbitrary lattices of skyrmions and antiskyrmions, which would be also first, at least in the simulations, and I hope to see them also soon realized. And the idea is that we can also use this to, so we can delete them or write them using pulses of magnetic fields, but you can also use spin transfer torques. So you can apply an AC current, and it will do the same job because you can reverse the magnetic core also using a spin transfer torque, even spin orbit torque and so on. And maybe for me the most interesting part would be that we can also move them, so they are not pinned under the nanodots. If you apply a current, you can just move them, and a new skyrmion will be generated underneath, because the vortex core generates the skyrmion, not the exchange interaction. And then if you move the skyrmion underneath, a new skyrmion will be then imprinted, because that's the ground state. And the very nice part would be then now, so we are working right now to realize this also experimentally with the movement, so I hope to be published also soon. But the idea is that in the case of the anti-skyrmions, you can rotate them a bit, right? And then you can apply the current in the 45 degrees, and you can get rid of the Hall angle. So because if you apply the current, so along this direction, you'll have the Hall angle. But then if you put your cross 45 degrees and you apply the current to that 45 degrees, then you don't have a skyrmion Hall angle. So you can propel the anti-skyrmions straight forward. So thank you very much for your attention. I hope that's it.
Yeah, thank you for the nice talk. So, yeah, Matthias.
Yeah, thanks. Oh, wow. A very nice talk. Just one comment on slide 15, where you say that the topology doesn't, well, the topological winding number doesn't change sign. If you go to 0, you already have to nucleate a Bloch point. If you go from 1 to 0. So it's not just sign change. I think the important thing is that it stays at finite value with the same sign. Because going to 1 to 0, you need to nucleate a Bloch point.
But this is the point. So this does not. So you really don't get a Bloch point, because the total one. We looked into detail in this, because as you know, detail he was very easy. These are possible.
Yeah.
So we looked into detail into this, and then it really does not build a Bloch point. But it might also be that we have a too large of discretization. That's why we don't see it.
Okay. And then in slide 5, just something that I saw that I didn't see in the talk yesterday. it looks like some of the objects that you have seen here, yes, they seem to be linked. So if you look at some of the objects, there seem to be some contrast even in between exactly.
Yes.
So this means that they are also not free to move independently.
They are, but this is basically, so it's the snapshot is taken at 80 millitesla, and then so there was a stripe domain here, and this stripe domain most probably collapsed at 79.5 millitesla. So now it's just, I took the snapshot exactly when I saw that they are enough structures. So if you increase the field like 0.1 millitesla, then you also get rid of this, so they're really isolated.
Okay. All right, thanks.
Any other question maybe online or no? So for the stabilization that you use, I mean that you employ this permalloy to stabilize the skyrmions, how would they be stable after you try to move them out of the dot? So how?
So this is the main idea of using a skyrmionic layer underneath, because as you can see here, the skyrmions are also stable without having any vortices. So if you have, you use the vortex to nucleate it at a certain location, but when you move it out, you basically are in this system. So where you do not have any vortex on top, right? But in this system, it's also stable. So if you have in this artificial skyrmion lattices, they use this 1 nanometer PMA stuff, which cannot host the skyrmions outside of the vortex. So it's just an imprint of the exchange interaction, basically. But what in our system, you go out and you're in the skyrmionic system where you can just have the skyrmions and the skyrmions all the time.
Okay, so there would be some energy barrier to, annihilate the skyrmion itself. Okay.
Exactly. Yeah. So we also calculate the energy barriers, also very high. But again, this is the problem. You calculate energy barriers using micromagnetic simulations the way we do. It's inaccurate because you usually have to go over block points, and then you cannot describe them micromagnetically because you have antiparallel lattice.
Okay. So we don't have any other questions, so let's thank again the speaker.